Okay, so welcome to our session for today. We are going to discuss now the integration of section modulus in our flexure formula. So we really need to integrate section modulus because we are dealing with the dimension of beams if we deal on the beam stresses. So we recall now the formula for our flexure formula, the general formula. So we have this general formula. So recall that we have three sides of the equation here where we have m over I to be equated to the stress all over y is equal to the modulus of elasticity all over the radius of curvature. If we are concerned with beam stresses, we need to relate m over I, this stress all over y, because we are dealing with the dimensions. So we are going to pair this to that side because we are not so much concerned with this elasticity and radius of curvature, and hence we can write this formula. So from the flexural stress is equal to my over I. Y here is the distance from the neutral axis of any layer of the beam cross section, and it will be the farthest at the extreme fiber. So we note here that the farthest distance from the neutral axis is located at the extreme fiber, so either on top or on the bottom of the cross section. Therefore, your flexure stress is at full strength at that location. So by that, we can have the maximum flexural stress equal to mc over I. So we'll just replace y by c, wherein c is the farthest distance. And then we have these variables such I, c as the dimension requirements. This is where the section modulus will come in. So section modulus is one of the geometric properties of steel shapes. So it is being incorporated in the flexural stress since it is the intention is to simplify the solution on flexural stress because there are a lot of sections, and we have experienced that there are tedious procedures in coming up with the I, the section modulus, the centroid, and among others, which we need in the design. So geometric properties of steel shapes is already available on several references. Originally from AISC, we have this. Let me show you a sample. So we see here an appendix wherein we have a wide flange section of W shapes. This is in terms of FPS unit. And normally it is designated by its depth, the overall depth. So as we can see here, W24. 24 here is usually the overall depth, and then this is the unit weight, 104 pounds per foot. So therefore, in every foot there is 104 pounds for this particular section. And then the depth is given, the area is given, the web thickness, the flange properties, the width of the flange as well as the thickness of the flange. And then for the x axis, y axis, given are moment of inertia, the section modulus, the radius of gyration. So as we can see, there will be a complete set of geometric properties essential for the design. So there are a lot of data here wherein your needed dimension is, or needed parameters or variables are already computed in a table. So we can see a variety of shapes here. So first we have a wide flange. By the way, the outer dimension or the outer stem is what we call flange, and the inner stem is what we call the web. Okay, and it is assumed that your x-axis is the horizontal line, and then y is the vertical line. Essentially, this axis is located at the centroid. So in this case, your plane axis is just at the mid, because this is a symmetrical shape. Okay? It is where your I is measured. Okay, so you do not need to transfer or use the transfer formula for this I bar or X bar. So if we are going to illustrate this, say this is the X axis. So if this is the X axis, therefore we are getting your I bar X. Okay, and similarly, if this is your center of gravity coinciding with your centroid or the center of gravity, we have this as I bar Y. So meaning if we have here bar, your I is referred to the centroidal moment of inertia. So x axis here refers to I bar X, and y axis is I bar Y. So this is a sample of wide flange section table in English unit. We also have a lot of table here or available for the SI system. So here is an example of channel. Okay, so usually C15 here refers to the overall depth. As we can see, 15 is the depth, so all of those are the depth. Okay, and this one is the unit width. So that is how to interpret the designation notation for different shapes. So another example would be a channel bar and then an angle. So here we have the table in terms of SI units. Again, your inertia, section modulus, and radius of gyration are presented on different various shapes. So that is for the table. And we go back to our topic, the section modulus. So normally there are two types of section modulus. We have elastic section modulus denoted by S, wherein S is equal to moment of inertia divided by Y. So we know Y is the distance from the neutral axis to any layer on the cross section. So meaning your section modulus is not at full strength at this type. So in plastic section modulus, we have to denote that by Z, and it is equal to I all over C. So notice that we just have replaced Y to C. And remember that C is the distance from the extreme fiber to the neutral axis, wherein it is the farthest distance along the shape of the property or the geometry. So therefore, plastic section modulus is a section modulus wherein your strength is at full because your distance is at the farthest. And from this, we can relate these two as a shape factor. So the larger the value of the shape factor, the better, because it has a great resistance since your C implied that we have a sufficient section modulus, and then that will be divided by the elastic section modulus, and that will be the shape factor. So we are still on this formula, however, we just have to inject or integrate this property to simplify our solutions in beam stresses. So let us have examples now. Okay, so let us consider this problem. Cantilever beam, 4 meter long, is composed of two C200 by 28 channels riveted back to back. What uniform distributed load can be carried in addition to the weight of the beam without exceeding a flexural stress of 120 megapascal? If A, the webs are vertical, and if B, the webs are horizontal. So we refer to Appendix B of the textbook for channel properties. Okay, from that appendix, we obtain this data here. So for C200 by 28, it has an area of 3,560 square millimeter. We have the width of the flange, 64 millimeter. The section modulus along the X is equal to 180 times 10 raised to 3 millimeter cube, and the I, moment of inertia along Y, is 0.825 times 10 to the 6 millimeter raised to 4. So here, let me have this as our center of gravity. Okay, now on that center of gravity, our section modulus is computed. So remember that the section modulus given by your Z is equal to I all over C. So basically, your loading is against the vertical, so therefore we need to consider here the centroidal moment of inertia along X. Okay, so I bar X along the center of gravity. Now, this channel is not a symmetrical property, and it is located somewhere where the neutral axis along the vertical is not symmetrically placed or located on the section, meaning there will be a distance from this fiber or the extreme fiber of this side up to the center of gravity, that is named as X here. Okay, that is named as X. So why do we need to locate that? Because if you're going to bring your channel in an upright section, or just invert the axis, we will be needing this X because we're going to transfer your inertia from the center of gravity. So there's no problem with regards to if the flange section wherein the webs are vertical. We'll just have to bisect this. Okay, and this will be our y because obviously the center of gravity lies within the center or the joining portion, since the channel is symmetric. Okay, and of course we'll just have to get the mid of this portion, and this will be our x. So this is our x, and this is our y-axis. So therefore, your section modulus given here, x is derived by I bar x all over c. So this one. Therefore, we have this value 180 times 10 raised to 3 millimeter cube. And for the webs wherein the section is in upright position, of course, this will be our center of gravity. So horizontally it is symmetrical and vertically it is symmetrical. However, in our given formula, we need to determine the distance. Okay, why? Because from this original data, your IY here, I'll just place it IY. Our IYY here is not located on the combination of these two channels. So meaning, your IYY lies beyond within this point, okay? And the other I is that one. So meaning, if this is the neutral axis along the y direction, we need to transfer, okay, say this is your IYY, which is now I bar x, okay, sorry, IX for that particular section, and this neutral axis is referring to I bar x, okay. So remember your transfer formula, that if we need to express your I in terms of the centroid or centroidal moment of inertia, we'll just have to utilize this formula, Ix plus AD squared. So no problem if this one and that of the Ix will just coincide to one axis or to one line. However, in this case, this channel, this particular channel on the upper channel is located at a distance x, okay. So this one, so this is actually distance x from the neutral axis, and so with this, and x here would serve as your transfer distance because the inertia computed here will just have to be transferred to the neutral axis because we need to express our I or the moment of inertia along the center of gravity. So that is the principle. So first, everything is given here, so all we have to do is to have the principle, and the principle is that we need to utilize this formula. Bending stress is equal to mc all over I. Okay, so I over c, this I over c, so just we have to invert this one, is z, right? So therefore the bending stress would be equal to m all over z. So just divide your moment divided by the section modulus. So the first question, uh, what uniformly distributed load can be carried in addition to the weight of the beam? In addition to the weight of the beam. So of course, your beam composes of two loading. Okay, the self weight, say I'll just have W as the total loading or the total distributed loading, composes of the self weight. So let me denote that as WDL or dead load, plus the additional loading, say we designate that as W live load. So W live load here is unknown if your webs are vertical. Okay, so that is the first condition. I'll just place here that this is letter A, and the second condition, we just have to invert your axis. This will be your letter B. So the first thing to do is to determine our moment value. So basically, we have here a cantilever beam uh, solution. Say we have here the cantilever beam. Okay, and this is loaded with the combination of the live load and the dead load. See, this is our W, and this is 4 meters. Okay, so we established the moment diagram in order to come up with the maximum moment of this cantilever beam. And basically, if you have a cantilever beam, just remember that your maximum moment lies on the support itself, because here we have three reactions, you know. We have R, say if this is A, this is RA, RAY, RAX, and your counter moment here for a fixed support. So the maximum moment at this type of beam, cantilever, is located at the fixed support itself. Okay, so therefore, we will just have to take moments at A to come up with the maximum moment, MA. So this is the maximum moment actually. So summation moments A is equal to 0. Okay, perhaps we can resolve this to 4W, and your distance here is the half of 4, that is 2 meters. Okay, so therefore, by taking moments at A, we have negative MA plus 4W times 2 is equal to 0. So we further get MA in terms of W, so this is actually 8W. So upon getting your moment or the maximum moment, okay, so let us note here that this is the maximum moment. We'll now employ this formula. M all over Z. Okay. So we are basing here our loading through the maximum flexural stress of 120 megapascal. So all we need is to substitute. Okay. 120. Our moment is 8W. And our section modulus along X is this one, 180 times 10 cubed. 180 times 10 cubed. And there are two sections of this channel. Okay, so if you notice that there are two of them. Okay, so this data, basically this data is for this channel. So this is letter A. The letter A is a combination of a back-to-back channel, wherein the channel is having a data of these properties. That is why we are multiplying it by 2. So in here we can get the value of W immediately. So in here we will have 5.4 million Newton per millimeter. So we can write this as 5.4 kilonewton per meter. And as for our live load, we'll just have to write it again. We have W dead load plus W live load, and this is 5.4. Okay, that is equal to the dead load. Basically the dead load here is the self weight. What is the weight here? C200 by 28. So if we recall back our table, this is the overall depth. Okay, overall depth H, and this is the weight in kilogram per meter. So therefore we can now determine the dead load. Just multiply this by 2 because there are two channels. So we have 2 times 28. However, this is in terms of kilonewton. Okay, and we need to express 28 in terms of kilonewton. Okay, so we recall how to express kilograms in terms of kilonewton. So first, how shall you translate kilogram into newton? Of course, we'll just have to multiply this by the acceleration due to gravity. This is meter per second squared. So this becomes newton, okay? And there are 1000 newton in 1 kilonewton. So basically our conversion factor is 9.81 all over 1000. And we'll just have to place it there. So we will obtain now the distributed load or the additional distributed load aside from the self weight, okay? And so we will have here 4.85 kilonewton meter. So that is for the condition letter A, wherein the combination of these two channels wherein the webs are vertical. So if you're going to invert the section, that is the condition for letter B. So we use the same formula and we use the same maximum moment because it has nothing to do with the cross section. So only that the variation is along the section modulus. So in your data, it is not readily available on y-axis. Why do we need to use y-axis here? Because if this is inverted, your y-axis becomes, or this moment of inertia becomes your ix for the independent channels here. So we need to transfer it along the neutral axis using this formula. So that is the sequence of our solution. Okay, so we have I bar x. So I bar x, here it is, I bar x. We have ix plus ad squared. So I bar x, we have two of them. Okay, there are two. So ix is actually iyy. That is equal to this value. Okay, 0.825 times 10 to the 6. Okay, so we add the area, 3,560 to this area. Times distance from the neutral axis, or the transfer distance. So it is the value of x. So x here is 14.4. Okay, so we compute that I bar x is equal to 3,126,403.2 millimeter raised to 4. Okay, so using this formula, sigma is equal to mc all over I. If you want use z, which is I over c, because z here is not readily available, we can compute for this one. Anyway, we can directly use this formula without having the section modulus. So the moment, or the allowable here is equivalent to 120 megapascals. So we have 120, and then the moment here is in terms of W equivalent to 8W, and the C, or the farthest distance from the neutral axis. What would be that one? So if you investigate here, this is our neutral axis, and that the farthest distance from the neutral axis would be the width itself. Okay, this is actually the width, 64 mm. So that is 64 millimeter. So this is the neutral axis. This is the outermost fiber, or the extreme fiber, that is equal to 64. So this is also applicable to this. Okay, so we'll just place 64 millimeter here, and then this is the I, 3,126,480.2. So therefore we can get the value of W equal to 732,750.75. So this is supposedly Newton per millimeter. So again, we convert this one so that we can incorporate this to the dead load. Okay, so W dead load plus W live load. So we need to express also our W in terms of kilonewton. Okay, so all in terms of kilonewton per meter. So we'll just have to divide this by 1 million, just like what we did here. So W is obviously 0.73275. So substitute. WDL is that one, 2 times 28 times 9.81 all over 1000. So we are looking at the additional load aside from the dead load. So we have 0.18 kilonewton per meter. So these are the additional loading aside from the dead load that these two beams, or the beam, could carry. So as a comparison, we can see here that the web which has an upright position will have more resistance to loading, okay, or to the bending. And if your channel is on this setup, wherein your web are in a horizontal position, it could carry lesser than that of the webs that are in upright position, or webs are vertical. Okay, so the lessons learned here will be that on bending, the depth, should prevail, okay, the depth along the loading should prevail against the width. Okay, so letter A has a greater resistance to loading as compared to B. So in fact, we have already proven that on this computation, or in there is a significant difference on the loading, and this setup is much more recommended in terms of carrying a flexural loading or flexural stress. So this is the solution for this problem. So anyway, these data are given in the table. So with this, let us try another example. Okay, so let us try this example. So this is a combination of two flange section, or we have S18 by 70. We are going to calculate the maximum value of WO if the flexural stress is limited to 20 kips per square inches. So we make sure to include the weight of the beam. So first, we need to determine the data. Okay, to acquire the data from your appendix table, properties of I-beam section on the US customary units. So from that, we obtained S18 by 70 that is having a section modulus of 103 cubic inches. So probably you might ask, don't get confused here that only in this book that it is designated by S. So supposedly what we have introduced is this one should be in terms of Z. Okay, so we will take off from this formula. Of course, that is M over Z, and then of course we will be needing your moment here, and substituting the values, we have this as allowable 20. That would be equal to M all over 2 times 103. So 103 is doubled because we have here a combination of two steel sections. So out of that, we can determine right away our moment equivalent to 4,120 kips inches. Now if we convert that, so we need to convert this kip inches into kip foot. So the conversion factor is 12 inches. Sorry, we should kip inches. So there are 12 inches in a foot. You just have to divide this by 12. So 4,120 divided by 12 is actually this 1,030 all over 3. Okay, so why do we need to convert it into feet? Because by and by, we should pair that with the formula of W out of the maximum moment. So the maximum moment now shall be derived out of this load diagram, and then come up with the shear diagram, and then the moment diagram. Okay. obviously this is just equal to 18 plus 6 24 30 W. So if that is 30W, 30W will just be shared by these two. We have 15 each, so that we're going to utilize that on our shear diagram. So first, start from left to right. For the leftmost portion, we consider this area first. So that is actually 6 by W, and that is going downwards. That is why that is a positive or negative value. So negative 6W plus 15 units upwards, we come up with 9W. And then we deduct this portion. Okay. And that portion is 18W. So from 9W, we subtract 18, we have negative 9W. And then we have here the pointed load at this point. So we have 15 units upwards. Therefore, this is 6W, and then 6W, just close it out to 0. Okay. So we'll just have to get the area here. 6 by 6, 36 all over 2 is negative 18. Okay, so from that negative 18, we'll just add this triangle. So 9 by 9. Okay, 9 by 9, 81 W all over 2. So actually this area is 40.5. So 40.5 minus 18.18 W. That is actually 22.5 W. And this, so far, this will be the maximum moment, 22.5 W. So this will deduct from 22.5. So it will yield to 18, and then it will close to 0. So this is decreasing, concave downwards, okay, and then decreasing, concave downwards, and that is concave downwards, since all of the gradient are decreasing. Okay, so out of that, we tend to equate the obtained value. Okay, so your moment here is 1030 all over 3. So this one, we equate it to the maximum, which is 22.5 W. So therefore, 22.5 times 3 divided by 1030, that is 15.26 kip per feet. Okay, so that is for this problem. Okay, so simple as that. We'll just have to incorporate section modulus and the tables here. Okay, so next, let us have another example. By the way, unknown here is to solve the additional loading aside from the dead load. So similarly in the first problem, we just have to substitute here. So 70 years that is the weight in pounds. Okay, So this shall be in terms of pounds. This one. And we need to multiply here 1000. Why? Because in 1 kips there are 1000 pounds. So we do this in order to jive with the pounds here. So you just have to deduct 140 from this. Therefore, finally, the additional load would be equal to 15.12 kip per feet. Okay, so next problem. A beam with sections S310 by 74 is used as simply supported beam 6 meter long. Find the maximum uniform distributed load that can be applied over the entire length, in addition to the weight of the beam, if the flexural stress is not to exceed 120 megapascal. So this is a similar situation on the previous problems. So of course, we refer to the data first, and then come up with the maximum moment. So anyway, if we have a simply supported, we have already introduced to you that the maximum moment is equal to W L squared all over 8. Okay, so that the maximum moment is equal to W times 6 squared all over 8. So 6 here is the length. Hence we have 4.5 W Newton meter. Okay, so here it is. So next, of course, we are going to use the allowable by this formula, moment all over section modulus. And section modulus already available on our data, so we'll just have to multiply. Okay, so 4.5 here shall be multiplied by 1000 because we need to express our meter into millimeter because of our given is millimeter in terms of millimeter. So by that we cross multiply, divide, and come up with this value, 2264.36 kilogram per meter. So just the same, we will have to use this, that W, okay, W of the dead load, the self weight plus the additional loading aside from this. So from the maximum moment down to W, so we substitute W here, and then just consider the weight in kilogram. This is it. Okay. So 74 kilograms. So 74 kilogram is directly substituted. And then in here, we have 2264.36. Actually, answer your answer a while ago, 22,000 shall be multiplied by a factor. Okay. So in order to come up with a kilogram unit, we just divide that by 9.81. Sorry. should be kilogram and that would be Newton. So we come up with this value and then apply it in here. So we will have a live load of 2190.36 kilogram per meter, and that could be converted into 21.5 kilonewton per meter. Okay, so that completes this problem. Okay, so next, so another beam composed of two C10 by 30 channels back to back, simply supported at its end. The beam supports a central concentrated load of 12 kips. So we have here our distributed load of 1,200 pounds per feet, including the weight of the beam. So remember that this already includes the self-weight of the beam. So compute the maximum length of the beam if the flexural stress is not to exceed 20 KSI. So just the same, we will use the formula for the bending stress in terms of the section moduli. We have this one, I all over Z. So from your allowable, that is 20 KSI, sorry, this should be M. Moment all over Z. So our moment is yet to be determined. Your Z is actually that 20.7. So by cross multiplication, we have 414. And what will be the unit? Kips per meter. KSI. So from kips, this is actually KSI. KSI being multiplied by the area, 20.7 inches squared. So basically this is cancelled. So therefore this is 414 kips. Okay, so 414 kip here should be equated to the value of the maximum moment out of the beam. So where shall we get this maximum moment? Actually, we do not need to do shear and moment diagram, because if we have a symmetrically loaded beam and it is simply supported at farmost end, so this one, we'll just note that the maximum moment is at the mid. Okay, at the mid. So from that, I am going to have this as my cut section and consider the left portion. So considering the left portion, so this is 1.2. This one we're already derived as 6 plus 0.6 of L. And then you just have to determine the moment here. Okay, because the moment at that portion is at maximum, basically. So if this is point O, you just have to take moments at point. Say this is 1.2 times L all over 2. And this is basically L all over 2. So that if we take moments at O, we have negative M minus this one 1.2 L all over 2 times the half of L over 2. Okay, and then we add this moment with the momentum of L over 2. So this is equal to 0. And then we simplify this equation. We transpose this M to the other side, so it becomes positive. And then all of this will be retained. So this is 1.2 negative 1.2 L and L will combine. 2 times 2, 4 times 2 is 8. Plus this one 6 or sorry 6 over 2 is 3, shall be equal to 3 L plus 0.3 L squared. So this is equal to N. Okay, next. So we consider this as our LCD. So just copy that one. So this shall be multiplied by 8. So 24L. And 0.3 times 8 is 2.4 L squared. Okay, so from this we can solve or equate this to what we have obtained a while ago, that is 414. Okay, so 414 keep so let us be careful of the unit here. So yung 20 natin So what is the thing here? KSI. So if this is 20 KSI and this is inches, so therefore this should be keep inches. So if this is keep inches, we need to convert this in terms of feet. Okay. So how is that? We divide this by 12. Okay, so we divide that by 12. So to make our unit consistent, so we have 34.5 keep foot. So we now equate that one to this equation. So we have 34.5 times 8 minus 's equal to negative 1.2 L squared. So actually we can combine this already. So positive 1.2 L squared plus 24L. So basically we will have a quadratic equation for this second degree equation. Okay. So anyway, it will let us check our solution. So from here, it will not jive to answer in the book. So you can see here that we should multiply this by 2. Okay, because there are two areas here. There are two sections for the I beam. So supposedly this is 8 to 8, 8 to 8 inches, and then we divide that by 12. We have 69. 69 kips feet. So instead of 34.5, that should be corrected to 69. And then rearranging terms, we have negative 69 times So therefore, we can compute now the L. And L would have a two roots. First, your root here is neglected. And hence, L1 here is adapted as our required length in order for this beam to carry the loading given our limit allowable for flexural stress. So that's it for this problem.